Today's lesson is going to be graphing rational functions, and we're going to start with a review of factoring quadratic trinomials. So remember, in our quadratic trinomials, we're looking for the leading coefficient multiplied by that constant term. So for example 1, x squared minus 5x plus 6, we're looking to see what multiplies to 6 but has a sum of the middle term, which is negative 5. And those values would be negative 3 and negative 2. Since I do have a lonely little x squared, then the two factors become x minus 3 and x minus 2. Example 2, 3x squared minus 13x plus 4. In this example, again, we're going to follow that same process, and I'm taking leading coefficient times constant, what multiplies to 12, but has a sum of negative 13. So I can do 1 and 12, 2 and 6, and 3 times 4. 1 and 12 multiply to 12 and have a sum of positive 13. So if I make them both negative, then I will have the sum of negative 13. So I'm going to factor by grouping or busting that b term. So I'm going to take the negative 13x and write it as a negative 1x and a negative 12x, and the remainder of the problem stays as is. So 3x squared minus x minus 12x plus 4. We're going to factor by grouping the first two by factoring out their GCF of x to leave me with a 3x minus 1. And I'm going to factor the back two terms, put them in a group, and if that third term is negative, you typically want to factor out a negative. 12 and 4 both divisible by 2, but even larger is 4. So I'm going to factor out a negative 4. When I divide through or factor out negative 4, I'll be left with a positive 3x and a negative 1. So I got exactly what I wanted, an identical factor, 3x minus 1, and the GCFs, x minus 4, become your second factor for that trinomial. Great job, guys. Let's get on with today's lesson. Again, we're going to be graphing rational functions. We're going to look at all the characteristics that we have worked on up to this point, and then put them all together to create a graph of a given function. So remember, our domain is all the factors that come from the denominator set equal to 0. And we typically will write it in interval notation, negative infinity to the vertical asymptote, union the vertical asymptote to positive infinity. Vertical asymptotes are the denominators that do not reduce. When you set them equal to 0 to find those domain values, those leftover factors in your denominator are x equals the number for a vertical asymptote. X-intercepts, where it crosses the x-axis, are factors in the numerator that don't reduce. Make sure you write them as an ordered pair. And your y-intercept always has a 0 for the x-coordinate, so you'll substitute all x's in the equation with 0 and solve for your y value. Again, write as an ordered pair. Then we talked about the wholes of a function. You're going to look to see if any factors reduce. You'll set each of those factors equal to 0 to solve for x. That will give you the x-coordinate of your whole. Then you'll take this x value, substitute it back into any leftover factors from the original function, and solve for the y, and then you'll have your ordered pair x comma y for your whole. And then looking at horizontal and slant asymptotes. Remember, we are only graphing horizontal asymptotes. The slant you just need to recognize. So a horizontal asymptote will be y equals 0 if you have a larger denominator degree. Y equals the leading coefficients if you have the same degree. So biggest exponent in the numerator and denominator would be the same. And if your degree in the numerator is larger, then you'll have a slant asymptote. Again, we're not graphing them, we just need to recognize them. This is personally how I prefer to graph my rational functions. Before I factor anything, I'm going to determine my y-intercept. Then I can look at the horizontal asymptote. After I've determined those two things, I will then factor the entire equation, numerator and denominator, so I can state the domain, everything from the denominator, determine the vertical asymptotes, leftover factors in the denominator, determine the x-intercept, leftover factors in the numerator, and then as needed, I can use the table function in the calculator to get any other points. Our first example, f of x equals x minus 2 divided by x plus 2. Again, I first like to determine my y-intercept, so let each of the x's be replaced with a 0 and then simplify the y values. Negative 2 divided by positive 2 is negative 1, so my y-intercept is the point 0, negative 1. I will then look at the horizontal asymptote. So I'm looking at the leading coefficients that I have because the greatest degree in the numerator is x to the first and in the denominator as well. So I'm just going to take those leading coefficients, 1 over 1 equals 1. So my horizontal asymptote is y equals 1. And you'll notice as I determine something, I go ahead and graph it. Now I'm going to check the domain. Domain is everything in the denominator. The only factor down there is x plus 2, set it equal to 0, and that gives me x equals negative 2. That's actually the equation of my vertical asymptote because I didn't have any factors that reduced. So I'm going to go ahead and sketch my vertical asymptote at x equaling negative 2. Just do the best you can. Doesn't have to be perfect. And then I'm going to write the domain as negative infinity to negative 2 union negative 2 to positive infinity. Next, I'm going to determine any x-intercepts. So my x-intercepts are factors that are left over in the numerator, nothing reduced, so I'm going to set x minus 2 equal to 0 to get x equaling 2. So my x-intercept is the point 2, 0. So I'll pull out that point right here. And then I'm going to check for the holes, and we've actually already talked about this. There will not be any holes for this example because the factors do not reduce. So you'll notice on the bottom right-hand side, I can go ahead and sketch a curve because I have a y-intercept and an x-intercept. And from there, I'm going to approach the horizontal asymptote to the right and the vertical asymptote dropping down and to the left. You should be able to mimic these same values, or you can use a table function in your calculator. So from the point of intersection, I go to the right 2 and down 2 to get the y-intercept. So I'm going to do the exact opposite. Go to the left 2 and up 2. That would mimic the y-intercept. And then from this point of intersection of the asymptotes, I travel to the right 4 and down 1 to get the x-intercept. So I'll do the exact opposite. Travel to the left 4 and up 1. And then I've got 2 other really good points that I can sketch my curve through. There's your first rational function. Great job. Our next example, f of x equals x squared minus x minus 6 divided by negative x squared minus 5x minus 6. Again, the first thing I'm going to look for is my y-intercept. I let all of the x equal 0 and simplify for the y value. Negative 6 divided by negative 6 is positive 1, so my y-intercept is at the ordered pair 0, 1. I'm now going to look for the horizontal asymptote. And for that, I'm looking at the degree of the numerator and the degree of the denominator. They are both the same, raised to the second power. So now I'm going to look at those leading coefficients. 1x squared divided by negative 1x squared. 1 divided by negative 1 is negative 1. So my horizontal asymptote is y equals negative 1. I'm going to sketch that horizontal asymptote as I go. In order to get the domain, I do need to factor everything. The numerator, I believe we already factored in our warm-up. That is x minus 3 multiplied by x plus 2. And in the denominator, I notice that there's a negative in the front of everything. So I'm going to write negative parentheses x squared plus 5x plus 6 so that I get the correct factors when I actually do factor this. So I'll keep the negative outside. And then what multiplies to 6 and adds to positive 5, that would be x plus 3 and x plus 2. Hopefully right now you've noticed that there is a factor that reduces that will give us a whole. We'll get to that in just a moment. Before that, remember, domain is everything from the denominator. So when I set x plus 3 equal to 0, I get negative 3 as its value. When I set x plus 2 equal to 0, I get negative 2 as its value. So my domain is going to travel from negative infinity to negative 3, union, then between your two asymptotes, -3 to -2, union, and then -2 to positive infinity. Okay, our vertical asymptote is any factor that does not reduce in the denominator. But we do have something that reduces. We have the factor x plus 2 that reduces. So I'm going to go ahead and label that guy as a whole, and we'll come back to that one in a little bit. The factor that does not reduce in our denominator, x plus 3, gives me a vertical asymptote of x equaling -3. Go ahead and sketch that vertical asymptote. Again, draw it the best you can. X-intercepts are any factors that you have left in the numerator. And in this case, what I have left in the numerator is the x minus 3. And when I set that equal to 0, I get a positive 3. So my x-intercept is at the ordered pair 3, 0. So I'll travel over to 3, 0. Put my x-intercept. All right, now back to the whole. For the whole, that is the same factor in numerator and denominator. What reduces? The x plus 2. So I'm going to set x plus 2 equal to 0 and solve to get x equals -2. That is the x coordinate of my whole. I will then substitute -2 into anything left in the function. I have x minus 3 over negative parentheses x plus 3. I'm going to substitute a -2 for each of those to solve for the y coordinate. So -2 minus 3 would give me a -5. And the negative of -2 plus 3 would give me a 1. So I have -5 divided by -1. So y equals +5. So my whole occurs at the ordered pair -2, 5. So at -2 up 5, I'm going to put a big, huge gaping hole right there. There we go. Now you'll notice you have everything you need on the right side of the graph. You can connect your x and y intercepts, falling down towards the horizontal asymptote on the right, go up to the hole from the y-intercept, skip it, go past it, and keep approaching that vertical asymptote. In order to get a couple of good ordered pairs or values to plot, you would look at any of the values of x being -4 or smaller so that you could plot some points in this area in the bottom left. But remember, it should approach the horizontal asymptote, vertical asymptote and fall down, horizontal asymptote and flatten out, and basically take that particular shape. Okay, last one that we will do together, and then I'll have a second video of a few extra practice problems. Example 5, f of x equals -2x squared minus 8x, and that is divided by x squared minus 16. You'll notice in this example, I don't have a constant value at the end of the numerator, so if you need to put that +0, you sure can, if that helps you. Our y-intercept, let all of the x's equal 0, so I would get 0 over -16. That's just 0. So it's actually the origin, 0, 0. That should also be an x-intercept. I'm going to go ahead and jot that down here. I'll prove it to myself later. Next, we can look at horizontal asymptotes. So I'm looking at the degree of the numerator. It's raised to the second over degree of the denominator, also raised to the second. They have the same degree. With the same degree, I just take the coefficients. -2 divided by 1 equals -2. So my horizontal asymptote is at y equals -2. And again, I should have a y-intercept at 0, 0, which actually is the x-intercept as well. It's the origin. All right, let's factor everything. In the numerator, I recognize there's a GCF of -2 and x. So -2x is factored out. That will leave me with x plus 4. In the denominator, I hope you recognize that this is a difference of two squares. X squared minus 16 factors to be x minus 4 multiplied by x plus 4. Okay. Let's go through the domain. Everything in the denominator, each factor set them equal to 0. If x minus 4 equals 0, then x equals 4. If x plus 4 equals 0, then x equals -4. So my domain needs to go in numeric order from -infinity to -4, union, -4 to +4, union 4 to positive infinity. Now we are going to classify anything in the denominator as a vertical asymptote or a possible hole. And I've recognized that there is a factor that reduces. The x plus 4 factor reduces. Again, that's a hole. We'll come back to it. What I'm left with in the denominator is the factor x minus 4. When I set x minus 4 equal to 0, I get a vertical asymptote at x equals +4. So I'll go ahead and sketch that vertical asymptote. My x-intercepts should be anything left over in the numerator. I only have a -2x left in the numerator. When I set it equal to 0, I do get the x-intercept, the origin, as its ordered pair 0, 0. And last but not least, the whole. Again, there is a factor that reduces. X plus 4 reduces. When I set it equal to 0 and solve, I get x equals -4. That is the x-coordinate. Now to determine the y-coordinate, I'm going to substitute a -4 into any x's left in the equation. So I have -2x divided by x minus 4. That's -2 times -4, which is 8, divided by -4 minus 4, which is -8. So 8 divided by -8 gives me -1. So I have a hole at the ordered pair -4, -1 right here. There we go. Now you'll notice in this graph, we really only have two good points. We have the hole, which we can't use, we just have to kind of draw on the outsides of it, and then we have the origin as our x and y intercept. So from the hole going towards the left, I'm going to approach that horizontal asymptote and flatten my curve. I'll continue to the right through the origin and then jump up and increase as I approach the vertical asymptote. Again, you could mimic these points. So from the point of intersection, you'll notice that to get to the origin, I travel up 2 and to the left 4. So I should be able to travel down 2 and to the left 4 to get that mimicked point. And then I can sketch my curve approaching the vertical asymptote down and to the left and the horizontal asymptote up and to the right. And just do the best you can, guys. Again, you can choose any x values from the table, 5 and greater, to get any points plotted in that last section. All right, so this is the first part. We've done several together. I'm going to stop our video now so that we can take a quick break. You can practice a couple, and I'll come back with the remaining problems in this video, in today's lesson.